Okay. So today's lecture is going to be recorded on cloud, so you guys can access it later on after today's. I guess we have to wait for a while, maybe about an hour before it's ready. So today is gonna continue our last times on chapter 8, which deals with the MDS. And today's I'm going to show you how to use or design the system controller using another tools which we call the VEM. Okay. Okay. So basically, what we're going to do is we're going to design, as an example, a pop machine. Sellers, a pop machine. Okay, a pop machine or a pop machine, a pop vendor. Pop is a soda, right? A soda vendor. Okay, so we will start from scratch, something like that. And I hope you still remember the first step that we will do for designing anything is what? The first step, which is the most important thing, is what? First is to develop how to use it, or user manual, or you can say guide how to use it. Develop user manual, or how to use your products, right? Basically. Because this will give you the idea of the features, the function that you need for whatever that you want to design, and also the input, output of the system, what you need, and what it's going to come out, right? And from there, or you can say that this is what we call the empathy work. Okay, or you can say user requirements, right? And from there, then you can develop what we call the system model, or you can say system design, which is the highest level, or you can say it's the black box that contains the input output and also how it's gonna operate. So to determine what's underlining, for example, what kind of hardware you may need, what kind of software that you may need. Is this necessary that you're gonna need a computer, right? Or just microcontroller, which we're gonna talk about, microcomputer, microcontroller, or FPGA. And what kind of software? Can you use a software or whatever it is? And then from there, then you can go step down to what we call the component. Okay, design. Because usually when we design, we're not gonna design it as one piece. So we have many ways to do it. Like last time that we do is bottom up, right? Bottom up or top down. Oops. Sorry. Top down. Or mix between these two, right? Okay. And usually this will lead to what we call the hierarchical design. Which means that you start from the big system, okay, which has all the input and output, right? And what you're going to do, right? Or how it's going to perform. And then inside you can create a block diagram, right? I was going to go on, blah, 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 right? whatever. Okay, and inside this, usually it can contain smaller block, right? Whatever it is. Okay, so that's what we call the component. Okay, and or you can say a detailed design. Of course, and with each step that you draw, oops, is it? Okay, and each step that you use it, usually we want to do what we call testing. So once you design, you do testing, and you go back and testing. When you testing, component testing, then system testing, okay, to see if it's match usually. So it's going to be, yeah, you can do first step is simulation, right? And once work, then you can do creation or hardware assemble. And then testing your system, okay? And usually what we do is we will go back and recheck with this, which we call validation, or to prove that after you do the testing, it will give exactly the function of fulfill the features of a function as you written in the first place. Okay, so if it's not fulfill, maybe far off, what happened here? Far off, then you may have to tweak in design 2 or 3 or 4, right? So you can go back there always. Okay. So that's basically the steps to do all this, right? Design step. Okay, so you start off with number 1 to number 6 and then go back. Okay, so today's we're going to use the pop machine vendor, okay, a pop vendor machine, okay, as example. Okay, as you can see, once we reach the system design, we can also look at the system design, right? Then we can look at each component that we want. Component 1, component 2, component 3, and so on, okay? And in between this, then you have choice that you can develop yourself. Develop yourself. So you can say DIY. Number 2, maybe it can be the IP products, called IP products, or existing hardware. You can say that this is existing hardware that you may use. Then you have choice. Okay. For this, the pop machine vendor, we decided to use some existing part or component. Okay, because these components have been proven that it works like sturdy and very stable. Okay, so they produce it in mass, in quantity, so you don't have time to do this, and you probably won't be able to do it better than what they already produced. Okay, so let's see. First, for the machine vendor, what do you need? Okay, let's see. So we want to do a pop vendor machine. Okay, or you can say soda machine. Okay, so here we decided the function. Okay, it should be some easy pop vendor machine where you have a slot where you can put money in, coin. Okay, and then actually, yeah, there's a panel. Probably you can look at what they sell here, right? Okay, and after you put in the money, then the pops will drop, okay, into the open one, right? And then you can grab the pop, okay, that is came out. Okay, so that's usually the function of the vendor machine, all right? So you can see that the component that you need is what? The we call the coin receiver, right? We need number one here, coin receivers. Okay, number two, you can say the pop drop machine, pop drop machines where you can drop the pop. Okay, and number three, you need a coin exchanger in case that you put more money, right? Than what you need. Okay, yeah, there's another one here, right? I guess, and also the change here. Okay, so that's the chain came off. Okay, right, and that's the pop came out. Right? Okay, so these are a basic function. Of course, you can have more fancy function like that you can see here in everyday's vendor machine. You know, and it can do more than that. You can pay by, for example, you can pay by QR code. You can select many at the same times, right? But what we do is we're going to keep it simple here. Like number one is, okay, so you need a user manual, right? So number one, put in coins. Coins. Yeah. Okay. Number two is what? Number two is drop the pop. Okay, drop pop. Okay, coins. Okay, yeah, maybe put in coins enough to make a purchase. To make purchase. Okay. Yeah, number two, then if it's more, yeah, if too much, okay, the machine give you the chain. Okay, number three, drop the pop. Okay, so basically this is some things that very easy to do. It's use a very simple features. You can see that this is what only your machine can do. Okay, and actually, yeah, the requirements that what type of coins, yeah, that it can receive. Types of coin. You see, you have to determine what type of coins that it can be is, and I think there's only one type of string, right? And one price, one type of string and one price. Okay, so you can drop. I think those are requirements, right? And then process. Okay, so here you can determine that this is the kind of hardware that you need. Then we decide that we can use the components that exist, use existing component. Okay, remember that you need to protect the coin that you already have and also protect the exchange that you have, because then somebody might rob you from the vendor machine. So you have to protect that. So it needs like a safe or protection, right, for the money. Okay, that's why we decided to do this. And then the assembly, and then of course we need the controller, right? The system controller to do what? To manage all this. Okay, and also all this. It has to work in detail for this. Okay. Yeah, let's see if we can put it together. Yeah, like this, right? This the vending machine that you have. Okay, so basically, your system will look like this, as you can see, right? It's very simple controller. You have a coin receivers, okay, and then you have to design whether this one is enough or not. Actually, you have coin input, and then decided whether it's enough to tell the system controllers. Then the system controller go to the pop drop to tell the pop drop that, okay, you need to drop. And once it's dropped, the pop, then it has to tell the system controller that back that it's done, right? Drop. So you can say this is drop and then done. One is that you can say that enough, or you can say that enough, or purchase. Oh, no, sorry. This should be something like money that put in. You can say that amount of money that put in. It will decide whether this one is too much or not. It will wait for that. If it's too much, then it will tell this one to exchange, right? And then it will drop the coin, okay? Drop the coin, and then saying that done, okay? Let's go back there. Okay, so you can see the type of system controllers and also roughly the signals that involve that between all this design, right? Okay, so we decided to use the existing component for this tree. Okay, so but we need to understand how it operates first between the coin receiver, the pop drop, and the coin return. So this is one of the job. If you are using the existing components, then you have to study, especially the timing or the requirement of the signals that it need to be able to communicate with all these things. Okay, so let's go to the first one. Yeah, the first one is the coin receivers, or CR1971. Okay, so this is CR1971. Yeah, the pop drop is, I think, PR, something like that. The pop drop is PD, right? 1971. And coin return is CC1971. This is CC1971. As you can see, the controller has to understand and generate the signals, okay, that need to be able to talk to all these components, okay. But first, you need to understand the component first. Okay, let's go back there. So this is the coin receivers, okay. The coin receivers, it's of course there's internal hardware, or also existing whatever circuits, circuits set inside. So we don't care. What we care is what it's received and it's give out as a black box. Okay, as you can see, it receives the coin that you put in, right? And then generate the signals. Okay, so these are the signals that you need to talk to all the components here. Yeah, these are the signals that you need to send into system controllers, which are this, right? Which are this, okay? And it gives out what we call the coin presence, the $50. So this model can detect what type of coin that you put in, right? Because it's the coins varies in size, okay, and also shape, not shape, the size and the weight, right? And of course, there's no way that you can do that but yourself. That's why one of the reasons that why we consider existing parts or existing component, because you don't have to develop yourself. But what you're interested is what signals that it skips out and tell you, okay. Basically, you put the coin in, and this is the signals that we send to the controllers, or signals the other units that what type of coins that it receive. Then, of course, assume that it's getting in one by one. Of course, the slot usually will not be wide enough for you to put, for example, like 2 coins at the same time so that it's stuck. Usually it's not, right? And it has a sorter, whatever, and generate the signals to tell you what type of coin that it just received it. Okay, and you see it can receive $0.50, okay, a quarter, a nickel, which is 10 cent, right? This 10 cent. Okay, the dime is 5 cents, quarter is 25, right? And $0.50 is 50 cents. Okay, and then clear and coin presence. Coin presence means you receive the coin. So together with the type of coin that you receive, it will tell the system controller that it received money and how much. Okay, and then clear tell me that, okay, it's not busy. Okay, so it's ready for the next coin, I guess. Yeah, you see coin drop, you get command and clear. Yeah, and these are the signal description. Usually if you operate, usually you have to connect the power in, right? And with the program inside, if you generate the signals, which is digital, of course, but it's related to the analog sense. Usually this will use 5 volts. So plus minus for between 4.5 to 5.5 volts for the clear signals. Okay. For the duration of the depression of the coin release. Okay. So basically, the coin will be stored here, I guess, and detected. And once it's done, it will drop that into the model. Okay. And then coin presence, and then $0.50, 75. Okay. And these are the signals that involve, as you can see, the coin presence and also $0.50. So once you drop the coin there in the slot and it's getting whole, okay, it will generate the signals according to the coin that present with the coin presence. For example, if you drop a quarter, then it's gonna look like this, right? Once you drop, okay, you drop a quarter, 2 cent Q, and this is the moment that is stored there, right? Then after a while, this coin present will go up, right, and then go down, and then if it's quarter, then $0.50 will be stay low for a long time. Quarter will go up, right? Quarter will go up here, right? And then go down before that. And the rest will be like 0, right? Something like this, okay? And this is like 150, this is what it tell you. And this is 50, between this edge is 50s. So that is for any signals, right? And that to 50 minimum, right? So it's greater than 250 milliseconds, okay? And this is like less than 500 milliseconds, okay? Not more than. So those are typical 300. So these are the signals that generated by the CR1 1971, right? Okay, and next component is the coin changer or CC1971. Okay, to make this one easy for the change, so we are not calculating those, and we just have just one type of return, one type per bit. Okay, so when you return, so this another one can return only in 5 cents or dime. Why? Because this is the smallest unit, right? So you can change back into any values that you want. For example, if you have to make a 15 cent change, you just drop 3 coins, right? Or if you have 10 cents, you just drop 2 coins. So it's very easy for you to count the times that you need to drop it, right? That's depend on the, but every time you receive it, you just drop 1 coin. So if you have to drop 3 coins, you just tell you 3 times. You drop three coins, for example. Okay, yeah, and those are the meanings of the coin changer. So the coin changer is very easy. Okay, as you can see, timing detail. So if it's received the eject nickel, as you can see, it's received input to tell that to drop or to eject 1 nickels, right? Yeah, 1 nickels is 5 cents. Yeah. Yeah, nickels 5 cents, right? Usually, oh, nickel is 10 cents. Sorry. Oh, dime is no. Dime. A dime is 10 cents, right? A nickel is 5 cents. Sorry. So that's 5 cents. Yeah. Okay. Okay. Sorry. Yeah, nickel is 5 cents. Okay. So every time it receives a signal, it will drop 1 nickels or 5 cents. So, for example, if you have to make a 15 cents change, then you have 3 nickels in a row, right? So that's 1 drop, 1 coin of 5 cents, another coin of 5 cents. So basically, you ask the unit to drop 3 times, okay? And every time it's done, it will go back to the ready state. So it's still the controller that, okay, I drop it and I'm ready to drop another one. Okay, so the timings look like this. Eject nickel, right? Okay, once you receive the signal eject nickels, so this tells you that this will generate or is the cost of the next edge. It will cause the ready to drop, which be that a busy, or you can say this is busy dropping. And once it's dropped the coins, it will go back there. Okay, so it's done. Okay, but to eject a nickel, you need at least 10 milliseconds before you can drop this. Okay, so basically, like I said, you have to drop 3 times, right, for 3 nickels, for example. Okay, so those are requirements. Okay, and then the pop drop mechanisms, right? Same thing. Once you receive the drop pop signal, it will drop the pop or the cans, right? And then go back to pop drop ready. So the signal is pretty much the same thing, just change eject nickel and ready into drop pop and pop drop signals. Okay. So it's going to be like pop drop, drop pop, pulse rate with 10 minimal. So this is like 10 millisecond minimal. And same thing, ready line. Go back. Okay, ready, and drop pop. Okay, so pretty much the same thing as the CC or coin exchanger. Okay. Next, like I already said, so you need a controller that talking to all the units, right? And then communicate and also determine what to do next once you receive all the information and generate the signals that require the sequence of events that's going to happen. Okay, so from there and from the user manual, then you have to create the steps. Like I said, from the steps you can create the flow chart like this. Okay, from here. Okay, like this. Okay, you can create the steps so you can make it into a flow chart, right, of what happens in sequence. Okay, like this. So this is what we call the first flow diagram or flow chart. Okay, that's has to do with this machine. So for example, you start off with the power up reset. Okay, once it's power up, then it's ready, right? Waiting for the coin. So if you receive a coin at this step, if you receive a coin or not, if you're not receiving a coin, you just wait, right? So this wait. But if you receive it, okay, then determine values of the coin depends on those signals, and then add to the sum. So you need a sum here, right? You need variable sum to accumulate of the coin received, or you can say sum is sum plus coin received. Okay, the value. So is the accumulated sum greater than 30? Okay, so assume that the pop costs 30 cents to buy. Okay, the pop costs 30 cents to buy. Okay, so accumulated the sum. Okay, and if it's not enough, then you go back and wait for another coin, right? Until what? Until the sum is greater than 30. That is mean that, okay, you made the purchase, right? It's enough to make the purchase, so you go on, okay, and drop the pop. But before you drop the pop, you make the change first, okay? For example, if you put in 25, right, and then 10, so you have a total of 35, for example, then you have to make what? Make change 5 cents back, right? So in this case, you just check the sum. So if it's greater, if it's less than, go back, right? But if it's greater, then what? If it's greater, okay, then return, right? You can see that actually there are 3 cases, right? So first one is greater than or equal. Okay, so this is less than. Okay, so this is greater or equal, right? But test equal, which means no, mean if it's not equals, mean that's greater, right? And this side is yes, is equal. Okay, so you can see that if it's greater than 30, then drop the nickel and makes the sum equal sum minus 5, right? Okay, so you drop it until it's equal to 30. For example, like this, 35, you go round this by 1, and it's going to reduce from 35 to 30, right? And once it's equal, go and drop the pop. Okay, so that's the purchase done, then go back and wait again. Okay, so those are simple steps. And you can see these are very simple pop machine. Okay, and from the flowchart, then you can decode it or detail it further and make it as the ASM chart. Okay, more detail, you can say more detail as an ASM chart here. Yeah, you know ASM chart, right? Okay, from lecture with Professor Suri. Okay, the sanity is being power on, right? Power on. Once you power on, is enter state A. Of course, this is a state of reset. Okay, and then check for the coin presence. So it's directly it's fully detailed from both flowchart. Then you enter B, state B, and of course you check the total of coin, clear or receivers. Of course, there's no detail here, right? Coin received determine the values. You have to express this out as a further states, right? Then determine if the coin is getting and what type of coin. Okay, so you make the sum. C is the sum. You can see the sum will be evaluated by this time, reach this state. Okay, yeah. And if it's not enough, right, less than, yes, you go back and wait, right? Wait until you receive a coin, and the CC is from the CC coin receiver CR, right? 1971 will give you the signals, whether what type of this is. Okay, so this is the sum equals sum plus coin received. Okay, let's already say it and let's go back. And of course, as you can see, greater, this is less than, right? No, yes. As you can see, less, you go back and wait. But if it's not, no, this is greater than or equal, right? And if it's greater than equal, yes, it's mean greater, and this side is equal. Okay, yeah, so there's only three types. And of course, if it's not equal, you can see there's more detail here, right? So you follow this line, okay? Yeah, pause return nickels. You can see we generate a pause to tell what? To tell the CC 971 to drop the coin here. So it's in this state, okay? And then wait for the changer ready, okay? So if it's not, then you keep this until ready, then stop this, right? And go decrease sum equals sum minus 5 here, right? And go back there again. Okay, so it's gonna check until what? Until you equal. Then you go tell the drop pop to drop, right? And then go back. Okay. And once you clear accumulators mean you set sum to 0 again. So waiting for another one. Okay, and then coin drop. Okay. All right. So these are translated from here. And in the project, I hope to see like this kind of step, right? From 1 to 2. Okay, where you can specify more details. And then from here, you can determine what type of hardware and also what algorithm that you need. Okay, but since these are already determined, for example, like this, and this. So what you have to do is you just created the flowchart for the controllers, right? What you need is just the controllers. You don't need the hardware because all the hardware is already done. Okay, so you don't need to create it on the hardware. For example, these are not things that you have to create because it's already created, right? So these are the stuff that you need to create. And these are the flowchart of what's inside the system controllers, okay? And you can determine what type of hardware that you need, okay? You can see here, so that the CR171, so this is the coin, right? Coin receiver. Okay, and then you have here, this is the coin changer, right? And this is the pop drop machine, pop drop. So these are the stuff, and the rest are the controllers, right? So these are the boundary of the controllers. Okay, if you compare this with this is what happened. Okay, the red and the blue. Okay. Okay, so if you consider each one carefully, you can see that this is the type of the stuff that you put in here. Okay, and what you need is here, you can see we need what? We need something to store sum. Okay, so you need some register sum, right? You need register sum, of course. You need adder because you have to be able to adder, and you also need to subtract, right? Subtract, adder, subtract. But adder, subtract can be done with the same thing, I think, right? Let's see, greater than equal. Can we do subtraction here? Compare. Okay, can we do this clear counting? Hold on. 50 vibes. Oh, okay. Yeah, understand what to do. Okay. So what the designing is, since we returning 5 anyway, and the 5 is the smallest unit, so we convert everything into nickel bits. You need add sub, you need comparator, because you need to compare, right? As you can see here, we need accumulator, right? Sum plus, sum minus, and you also need to compare whether this is equal to 30 or not. So you need comparator. So these are unit that you need. Okay. And what they do is you can simplify the mathematics by using 5 cents on nickel as the base. For example, if we count 5 cents on nickel as 1 unit, okay, 10 cents will be 2 units, right? 25 cents will be 5 units of nickels, and then 50 cents Hello, hello. Can you hear me? Hello, hello.
ได้ยินครับ
ตะกี้ได้ยินไหมก่อนที่จะตัดไปได้ยินไหม
ได้ยิน
ฮัลโหลโอเคแสดงว่ามีอะไรบางอย่างโอเคlet's go back to the okay let's go back to our lessons. Sorry, I think there's a problem with the network, so cut off, but the recording still there. Yes, yeah, yeah, still recording. Okay. Hmm? Okay. Right. Okay. What we done? Okay. Yeah. So we convert everything into units, right? So and we return the coins in unit of nickels. So everything is fine if we use units instead. So okay, as you can see here, so we use the code here for the units of nickels. 50 codes is 10 units. So that is 1010, right? So that's equal to 10 units of nickel, and that's equal to 5 to 2 and to 1 units of nickels. Okay, so we can add how much units of nickels that we have. For example, if you drop 25 cents, that will be equal to 5. And if initially we got 0, that will be equal to 5. Now you got 5 units of 0, okay? And you're going to reach the purchasing line if you got 30 cents, right? Which is 6 unit. Okay, 6 unit, right? 6 unit is what? 6 unit is 0,110. Okay, so that is 30 cents equal to 6 unit, 30 cents. Okay, yeah, as you can see, if you insert 50 cents, right? This one will be present, right? Oh, sorry. If you drop 1 nickels, that will be 5 cents. This one will be 1 only, right? While the rest is 0. Okay. Coin present is 1, of course. But coin present is going somewhere else. It's going into the sum is here. 175. So that's the sum. Yes. Okay. I'm back again. Yeah. Oh. Share again. Let's kick off again. Okay. Yeah. As you can see, you got nickel, you got 0,111. Okay. So then you have to translate from 0,111 into 0,001. Okay. And you can see this is the weight, right? Then 0 you get from here, right? And that is 0 you get from here, right? And then 0 and the 1, that will be equal to 1. Okay. The to use this is very simple. As you can see that to determine the W4, okay, from this one, W4 is 1 only when 50 code, which is equal to the 50 cent signal. Okay, let me use another one. This is signal 50 cents signal, which means that is this one. Okay, the 25 cent, this is equal to the signal quarter, right? And this is equal to the input signals. 10 cent is dime, which is this one. Okay, and 5 cent is nickel, right? Nickel. As you can see, this will be 1 only when 50 cent is 1. Okay, so W4 is equal to the signal's 50 cents. Okay, that's why W4 got directly from W4. Okay, and yeah, let me show you maybe a little bit more. Okay, and then the quarter is W3, right? Yeah, here W3 is equal to the quarter, right? W3, as you can see, it's only one here. And that signal is equal to quarter, so W3 is equal to quarter. Because if quarter is 1, then this one will be 1 or else. That's why the quarter is directly attached here. Okay, that's W3. Okay, so W2, as you can see, there's 2 1 here. And it can be 1 only when this is 50 cent or dime. Then you give you 1, right? So W2 is either 50 cents signal or dime. Okay, and that's why you get here is 50 cents, right? And then dime, and then all together and go there. This is how they generate the code. Okay, and then W4. Use another. Use one. W4 is 1 and 1, right? So it's 25 cents, or it's quarter signal plus nickel. Okay, and that's from this and nickels go there, right? Or together and together. Okay, so that's, you can say, recoding or encoding all the signals from these signals directly. Okay. Okay, and from there you add it with the stuff. So you clear first. This one is 0 in the beginning because you are clear. Assume that these are all 0, so these are 0, 0, 0, 0. And so added bit nickels, it will come out as what? 0, 0, 0 plus 0, 0, 1. So it's going to be 0, 0, 0, 1. Okay, but if you insert a dime, this will be what? Sorry, a quarter will be 5. So that will be 0, 1, 0, 1. So after you add it, will be 0, 1, 0, 1, for example. Okay, so and then you lock it. Once you add it, then you lock it. Okay, and that will be here. Another storage here. If you you have to keep this because before you send that, you have to compare with this, and you see 001 come out as 0001 again, right? And it's go into comparator. This is comparator. Okay, and this comparator are compared with what? With 6 unit, right? Or 30 cents. So that is 0. You can see that is connected to ground, right? So this one is ground, which is 0. This is open and connected to 5 volts here, right? So this is 5 volts. So that's the logic 1. This also 5 volts is open, right? Not connect to anything, but this side is connect to 5 volts, so it's connected to this line. So this is also 1. And this is connected to 0, so this is gonna be 0. As you can see, this is 0, 1, 1, 0, or equals 6 units, or 30 cents, right? And you got 001 compared with 6, but it's not equal 6. As you can see, it gives you three options, right? Less than, equal, or greater, and it send it to system controllers. Okay. So as you can see here, it's not enough, so it's gonna wait. When you put more coin, for example, if you put another quarter there, 0101, and this one is 001, is go back there, right? And then it add up to this. It's gonna be what? 0101. Yeah, you need another storage here because you cannot update it right away. It's gonna be a cycling, so you have to store it somewhere first before you update this one. And if you put another quarter, that will be 6. Came out as 6, right? 5 plus 1 that you have here, that's going to be 6. 0, 1, 1, 0. And when you store 1, 0, 1, 0, and then 0, 1, 1, 0, and you compare it, and it's going to be equal. So this one is going to be 1 and 0. Go in there into system controllers. Okay. And once it's done, it's going to say, okay, this is 30. So generate these signals, go there, right? And then generate pop. Once done, tell you, okay, it's done. Done. It will clear the accumulator to 0, 0, and then go back and wait. Okay, so this is the hardware of the system controllers. But if you put more than that, for example, if you put 50s, what happened? 50 is 10, right? Yeah, let me. Okay, so if you put 50s, you start off with 10 units here, 1, 0, 1, 0. Okay, 1, 0, 1, 0. So it's going to go out there, right? And it's going to reach this one as 1, 0, 1, 0. So you compare with 6. Okay, so this one is greater than 10. Okay, so this one will be 1, 0, 0, and then set into system controllers. So it's determined that, okay, so this is too much. Okay, too much. So you have to deduct that by 1, right? By 1. So yeah, how you can deduct that? Hold on. You send this one to drop the coins, right? And it's already done. So it's gonna reduce this by 5. By 5, which is subtract 1. Okay, sorry, I understand now. Sorry, this is the sum, but this is the up down counter. Okay, this is the up down counter. Okay, and loadable up down counter. So basically you just load it directly from there. For example, if this is 0, 1, 1, 0, right? This is 0, 1, 1, 0, and it's gonna come, oh sorry, 1, 0, 1, 0, right? So it's gonna come out as 1, 0, 1, 0. Okay, and from 1, 0, 1, 0, you tell them to count down. Here you can see to count down or decrement accumulators, or you say count down. By counting down, every time there's a clock in here, you can see the clock. This count up, count down here. Yeah, you need the clock. The clock, every time you see the clock, this one will go down from 10. It's going to be 9, right? 9, and then compare again. As you can see, this is still more, so it's going to generate another one to count down. 9 and then 8, right? And still more. It's going to go down to 7, right? Still 1 here. It's go down. It's going to send this one to count down again to 6 to 6 until you reach 6. And every time you count down, you send the signal to drop the change here. Drop the change every time, and then you generate this, and it came out. Okay, to count down until you reach 6. Then you drop this and clear everything. Okay, so those are kind of hardware that you determine to use this. Okay, you use up down counter to count, to subtract 1, because every time you decrease 5 cents, you decrease the count by 1. That's why they use the up down counter. Instead of subtraction, you can use that one. Okay, so the state that you need to do in the controller is something like this. And remember last time that we're talking about the MDS, mnemonic documented state diagram. So it's a state diagram that has more detail than state diagram that you have. Okay, so you start off with A, B, C, D, E, F, G. Okay, so A is weight. A is actually from here, from the detail flow diagram. This from 740. Okay, so you have A, B, C, D, E, F, G, right? A, B, C, D, E, F, G. As you can see here, state. State is defined by the rectangle, right? This is the state A, B, C, D, E, F, G. Okay, with these things as what? As the input, right? These are the signal name. Okay, the sum is greater than 30. The sum is less than. So these are the name of the signals. Okay, these are the symbols. This is not. This is not the Boolean. So this is the name of the signal. Yeah, they should have a better name for this because these are sometimes confusing. So these are the name together. Is you can name it as, for example, as S S S S S S S A, for example, or you can say less than or equal, right? Less than 30, you can say that SE30, SL30, for example, some less than 30, or you can name this SE30, some equal to 30, and this one is S greater than 30. Probably use this one is probably better, but well, of course, this is the whole thing is just the name of the signals, okay? And of course, the coin present, this is the input, right? For example, this is from coin present signal, and this signal is determined by this, like I said from last times. Okay, so you can convert that flowchart into MDS diagram. Okay, all right, and you can see this the pulse. This the name of the signals. That's the name of the signals, and these signals are required to control the hardware, like I already show you here. Okay. Okay, so next is to design the controllers. Okay, the software. So this is the software. You can say this is the software of the controllers or the states. Okay, you can see that you still need to determine how this react, right? To everything. Okay. Still, these things is what's inside there. Or you can say the software. You can use, actually you can use microcontrollers, but here we want to design the controller ourselves. Like I said before, you can start off with the highest level is probably like general CPU or the micro computer by writing software, purely software. Okay, so if this can work in time, okay, that's just define your timing diagram, then that's fine. Okay, that's probably like the quickest. You can say the quickest and easiest one. This is quickest and easiest because everything is done in software, right? But of course, the cost is high cost. Why is that? Because you have to buy the CPU, you have to buy the computer, but the whole thing is that just maybe too expensive, probably like more expensive than the other parts. So maybe not necessary. Okay. Then the second step is to use somewhere in between Hello? Okay. I don't know why. My iPad net Wi-Fi is not as stable as my computer. I have to keep in again the third time. Okay. The fourth time. Okay, the record's still there. So that's good. Okay, I guess I stop at number 2, right? Okay, so the easiest solution and the quickest is probably like the general CPU because it's already made. All I have to do is to write a software to control this, but of course it's going to be high cost because CPU is more expensive, right? Okay, and it's uh, not probably like as cheapest as other figures, but if it's not satisfied in terms of performance, okay, performance is, yeah, I forget to talk about the performance, right? About the performance, you can say that this is low performance, although it's fast, but it's still slowest compared with the other solutions. This is in terms of relatively lowest performance, but it's the easiest or quickest to develop something, okay? If you need a better performance, then you have to go into number 2 or FPGA. This is better performance, or you can say faster, right? But it's going to take more time to develop, okay? And the cost is still high, okay? And then go on. So the cost is probably higher as well, okay? But of course, it's going to be better in terms of performance. But if you want to develop it in like a very large amount, this is going to be cheaper, of course, because everything was stripped down to whatever you need. Okay, and okay, from these things, you can say that we can design our own controllers by using many methods, and one way is to design the digital circuits or the finite state machine, okay, that control all this. As you can see, there are 1, 2, 3, 4, 5, 6, 7 states, okay, 6, 7 state, okay, with all the signals involved like this, okay. The stars mean that these are asynchronous, right? I think this is mean asynchronous. Okay, so first, from the 7th state, like I said before, you have many decision to make. First, what we call the state encoding, right? You have 7 states. So how many bits you need? At least, if you want to design these controllers, how many states or how many bits of states or status that you need? You have 7 states, right? So you need at least 4 bits of code to 3 bits, sorry, because 3 bits can cover 8 states, right? 8 different states, okay, for binaries encoding. So you need at least 3 bits in order to cover 6 states, 7 states, okay? And we pick this 3 bits, okay? And the second decision is state assignment. Because we have many labels, right? 3 bits, you have from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So you have 8 possible code to assign to 7 states. You can see there are many ways to assign this, okay? And for this particular examples, we assign A to be 0, 0, 0, Of course, you can pick another one, but for this particular one, we use A for 0, 0, 0, B for 0, 0, 1. So this for A, for B, for C, for D, for E, for F. Okay, so if you put this state into the map, we call the state map. This is the location of each state. For example, A is 0, 0, 0, right? Okay, so this is state is ABC. Okay, state is ABC means this 3 bit is A, B, and C. The first bit, the most significant bit is A, and the least significant bit is C. Okay, so ABC is 0, 0, 0, so A is here. Okay, state B is here in the map. C, D, E, F, G, and you can just see that there is unused code, which is 0, 1, 0, right? This is never used. Okay, so this don't care. This means don't care. Okay, they're not going to use X, right? Because X can be confused with variable X. Okay, so that's why they use X, and they don't use minus or dash. So they use 0, this, but it can still be confused with 0 here. Okay. Anyway, so this is what we call the state map. Okay. And of course, the problem of state assignments, as you can see that we have freedom to choose and to place anywhere you want. Okay. But there's some principles that you have to be aware of. For example, if the state is adjacent, then they should be assigned as close as possible. What you mean as close as possible? Probably they should be adjacent on the map. What is being adjacent on the map is that you can see that the codes are different in just one place, or you can say one unit. For example, we assign A here and we assign B here. Okay? So you can see A is 0, 0, 0, and B is 0, 0, 1. So you can see that when the state change from A to B from your map, you can see that, hey, we need to just activate 1 bit. So we use minimal energy to just change from A to B. And that's the reasons that why when we assign the codes to each state, we have to consider this too. For example, A should be adjacent to B, right? And then B should be adjacent to C, as you can see here in the map, right? So these are requirements. As you can see, B adjacent to C, and C should be adjacent to D. C actually should be adjacent to D and F. But sometimes this is impossible because those are the case that already did. So of course, you cannot fulfill all of this, but do the best as you can. So you can try many ways and see what's the best. Okay. D should be adjacent to E and F adjacent to C. You can see C not quite adjacent to D and F. Right? But if you assign C adjacent to D and F, then you have to use these things and this thing, D, F. That may be better. I don't know. Let's say if you want to do an alternative, right? If you can try, okay, A adjacent to B, B adjacent to C, and C adjacent to D and F. I will adjacent D here, for example, and F here, right? And yeah, still, there's sometimes it's not possible because D is to E, right? D is to E, okay, and then E has to go back to A, which as you can see, there's no way that the E can go there, right? And F should be sent to G, so this must be G, and G is go back to C. As you can see, there's no way that you can satisfy everyone, right? Okay, so do as best as you can. Understand, right? Anyway, for this particular example, this will be our state maps or state assignments, or you can say state assignment. Okay. Next is to generate what we call the controllers or the signals. We call the DMAPs or next state map. Means that you need to control how to change the state from state A to B and B to C. How are we going to control that? Okay. And the way we can control that is to consider the input to those states, inputs to each state, to those states, how it's going to evolve from A to B and B to C. Okay. Yeah. We have to analyze. We call this analyze states. Yeah, let's see, analyze this one. Okay, first, we know that state A, B, C, okay, these are the flip-flop, right? A, B, C. These are the state, all state, which is A, B, C, all states. And then if you want to change the state to the next state, okay, you have to, what we call consider, I don't know if you still remember, we call the flip-flop excitation. So what is flip-flop excitation? Flip-flop excitation means that when you want to change the state from the old one to the new one, Q plus is the next one. Once you see the clock, okay, you see the next state, how it's going to evolve. For example, if the old one is 0 and you want it to change to 0, which means that basically you want to change from 0 to 0, what input that you need to put it in? For example, if you have a D flip-flop clock here, right? And this is D, sorry. And this is the input. Okay. And then you have Q as output, right? For example, Q, the old one is 0. And when the clock comes, the next state after the clock comes is still 0. What do you put in there? Of course, the flip-flop is very easy. What do you want to change? Then you put that guys in there. So if you want to change this 0, you put 0 in there. So once the clock comes, this 0 will jump in there. Okay. Same here, 0 to 1. So you want 1, you just put 1 there. Okay. 1 to 0, you want a 0, so you don't care what is very for, you just put 0 there. 1, 1, you just put 1 there. Okay. So this we call the D flip-flop excitation, right? Which is very easy. So basically the A or D is equal to Q plus. So whatever you want to put it in the future, you just put it there. Okay. So we want to design this. Of course, we start off with state A. State A. What is state A? State A is 0, 0, 0. Okay, 0, 0, 0. And where can state A go? State A can go to first, go back to state A, or proceed to state B, right? State A to A, which is 0, 0, 0, or to B, which is what? Which is 0, 0, 1. Okay, you see that, right? And that's the only way that you can change from state A to somewhere else, either to state A or B. You don't have other choice because you jump to somewhere else. That's the only two places that it can jump, either to A or B. Okay, so next you have to analyze. So you start off with A, which is 0, okay, but you landed on 0 as well, right? So what does it mean? It means that for this D flip-flop, you just put in what? The end is 0, so just put 0 there, right? Then you get 0 because it's all 0. It's going to be 0, same as B. So the A, 0. What's mean that? You just put DA, whatever there, to make change from 0 into 0 again. You just put 0, don't care, right? Again, here is DB is 0. Because it's always 0, right? Doesn't care. Here, you can see from DA, Okay, from DA, which is the first bit. DA is the first bit. You want 0, so you put 0 in there. Okay, so you put 0 in there. This is the 0 that you want to put in, right? And for bit B, which is DB, at this state, at the state A is here, right? This is the position of state A. This is the second bit of state A, or, right? Or you can say capital A, capital B, right? And this is state C, state A. The third bit, small a, okay. Yeah, right? Then because it's all 0, so you don't care. You just put 0 there. Okay. But DC or bit C, this is different. As you can see, it can change to either 0 or 1. Okay. But if you change state, only what? Only when you have received something, and that something is the input. Where's the input? The input is the coin present, right? So if the coin present is what? If the coin present is 0, of course, it's jumped to state A bar, as you can see, right? It jumped to state A again. But if coin 0 is 1, then it's jumped to 1. It jumped to state B. Okay, that's why you put CP, which stand for coin present. Okay, which stand for coin presence there. Okay, so if CP is 0, then you jump back to A. But if CP is 1 or real, then you jump to B. You can see, we can analyze this. And that will depend on the input. Okay, and that's why you got 0, 0, and CP there. Okay, of course, this is 0. No, it's because you don't care. Anyway, so you just leave, don't care there. Okay, let's try another one. Let's try state B. Okay, state B. Let's analyze state B. B can jump to B and C, right? B, state B. State B, which is 0, 0, 1, right? Can jump to state B. Oops. To state B, which again 0, 0, 1. Or C, C is 0, 1, 1, right? Okay. So how can we summarize this? As you can see again, from 0 to 0. So what did you put there? You put DA equals 0 there, right? Because you don't care. This is going to be 0 in the futures. So you can summarize that. You just put 0 there. Okay. So that's why here you got 0 here. Okay. That's the first bit. Okay. Let's try the third bit first. The third bit is 1 and you landed 1. So you don't care. You put DC equal 1, right? Anyway, it's going to be 1. It's going to change to whatever. That's why you put 1 there for DC. Okay. And for the rest, which is in the middle, you have a problem because change according to either 0 or 1, but you can just consider this. When it's going to change from 0 to 1, this is when there is an input that corresponds to this. From B to C, and that will be equal to coin present or CP bar, right? CP bar, which means that you need to put DC equal to CP bar. So if CP bar is not true, or it's going to say 0, then you landed back to B, as you can see here, landed back to B again, right? Yeah, so that's why you put CP bar here. Okay, let's try state C again. C, state C, and C, this is more fun. Okay, state C, which is 0, 1, 1. Where it's go to? It's go to what? It's not go to C, right? It can go to A. It can go to A, which is 0, 0, 0. or go to D, which is 110, or go to F, which is 100. Okay, so how can we do that? We have to analyze each bit one by one. Okay, let's first decide this. This is the easiest one. You can see 1 all go to 0. So what you put there? You put 0 there. So DC is 0. But anyway, it's going to be 0 anyway, right? No matter where you go. That's why you put 0 there. Oops. You put 0 there. Okay, you put 0 there. And then from 0 to 1 for bit A, A is probably like okay, let's try B first. Yeah, B probably C, clear B. The only thing that changed from B to B, it's gonna maintain 1 to 1 is what? Is when C go to D, which is what? C go to D, which is equal, right? Equal. So 1 will be maintained if it's 1 or this one, okay? Or equal to 30 cents, right? So that's mean that this is happen when sum equals 0, it's gonna jump there. So you put dB is sum equals 0. So that's the name of the signals, right? That's the name of the signals. Yeah, that's why you see equal there. Equals mean sum equal to signals. Okay, so they use equal sign here, and they use less than here, and they use greater as a signal name. You cannot use this though when you actually coding, right? You have to use something else. But for this one, you can use less than, equal, or whatever. Okay, so they use dB is equal to equal sign, right? That's the name of the signals. That's why you put equal there. Okay, you can see we put equal there, which means the signal, the name of the signals, which is equal. Okay, and now consider the last one, which is this one. See, it can go to 1 in 2 cases. You can see that. Of course, it's going to be 1. But for the number 1, if C go to D, what is it? C go to D is equal sign, right? Equal sign. But C go to F is what? Greater, right? Greater. So 0 can change to 1 if what? If either C equals is true, or this is or, right? Or greater is true. So that's why it's come out as equal plus or of this. Okay, that's the meaning of this. So that's the name of the signals, and this is the or. That's 2 variables, right? Equals and or and greater than. Okay, like I said before, the symbol that they use is not very good. They can use EQ for this, right? And less than LT, for example, for this. That might be better. Okay, but you can say this is equal plus less than, for example. Okay, and right. Okay, and next is the same thing. You have to consider this along A, B, C. Okay, let's move to D. Okay, D is easy, right? D is 110. Okay, steady. It's 110. So it can move to either D, move to D, which is 110 again, or move to F, E, which is 111. This is easy, right? Because as you can see here, you just move a, the a equal 1 here. Again, same, this you need 1 here, right? You need 1 here. So db is also 1. Okay, dA, dB both are 1. So you can see 1 here, 1 here. Okay, and 0 move to 1. Possible only 1 when it changed state from D to E, which correspond to popped up ready or PDR. So you need PDR here. Okay, so that's why DC is PDR. So if PDR is true, then it's going to jump to E. If it's false, then it's go back to D. All right. Okay, and here is corresponding one, right? PDR. Okay. And again, if you consider this, F to G 100 to 101, F state F to G to F and G, right? F is 100 and 101. Okay, so this is you need 1, right? And here you need 0. Okay, and here you need what? You need to jump there from F to G, and you can do because of change ready. So it's going to be change ready or CR. Okay, so dA is 1, dB is 0, and DC depend on CR. Okay, here, CR 1, 0. Okay. F and E to G and E to G and G to F, right? There's 2 more states. So you can see here, state E to where? It's okay because state E to it can jump back only to A, right? So E is 111 and jump back to A, which is only B. There's only one state that it can go, right? So you just put 0, 0 there, 3 bits. There's no problem here. Just put 0, 0, 0 in the table. Okay, so that's 0, 0, and 0 because it's the only place where it can jump. So you don't have to consider that. Okay, and G back to C. Okay, state G. And it can go back only G, right? No problem. G to C because it's the only state. So you just assign that state into 101 into what? 011. No problem. Just assign 011 there into the A, D, B, and DC. Okay, so you got 011 there. 011. Okay, that's how you generate what we call the next state or D maps. Next state map or D maps of all the states. Okay. Then you have to create what's inside logic. Okay, so now you are viewing the states and or the signals that going into the system controller. As you can see, these are the signals that go in there. Okay, and these are the signals that you have to generate, right? Okay, so once you get all these, what you have to do is you have to minimize Boolean logic into Boolean logic. But how do you want to do it? Because now you have also variables in the map. Okay, let me copy this. Maybe I can copy this. Let's insert. Sorry. I can't. What do I do? I have to capture it. Is it? Okay. Handwriting. Can do just this. Okay. Oh, okay. And just do screenshot. Okay, good. Good enough. Okay. Listen here. Okay. Okay. Next is I'm going to show you how to do the optimization. Now we get this map, right? So how do we get to these equations? We have to do it in 2 steps. First, yeah, let's try this one first. Okay, yeah, let's try one by one. Okay, let's try this one first. Copy. Okay, paste it here. Okay. We're gonna do 2 steps. First step, step 1, right? Step 1. Okay, step 1. First, we consider everything is 0 first, and view everything is 1, and all the variables in the tables are 0. So basically, we consider these are 0, these are 0, and all everything is 0. So this is what we get. It's gonna look like this, right? 0, 0, don't care, right? And this comes 0, 0, 0, 1, 1. So that's the first step. And view other thing as a 0. This or this variable are 0, but don't care still there, right? And then circling only 1, that is possible. Do optimization of this. And the best one that we can do is this, right? Or you can say that this is what we can do. Okay. And this step give you what? Give you what? AC bar, right? AC bar. This one will give you AC bar. Okay, so that's the first step. Then the A is first step, which is AC bar. Okay. Then the second step is when these variables are 1 in this particular cell, or you can say that when 1 at a time. If you have more than variables, 1 variables at a time, then you have to consider it 1 at a time. But for this one cell, you assume that this is 1, right? This position is 1. Okay, let's choose another one. Assume this is 1. Assume this is 1. And the rest is the same. Still as the same before. 1, 0, 0. And then circling it, when you consider this cell as a 1 again. Okay, so what you can see here is what? Okay, and yeah, the one you already do there is going to be the same, right? So you just circling this, but this you already done that, so you leave it there. So that's the only things that add on, right? And this is when this guy is 1, so that happen only when this cell is 1, which is A bar B, and this cell has to be 1, so that's 1 A bar B, and which is a dot. This has to be true or 1, which means that this must be 1 as well. Okay. Yeah, so that's why you came out as this. Okay, so you have to circling in 2 steps, 1 and 2. That's step 1 and that's step 2. Okay, let's try another one. Let's try another one so you understand this better. Okay, so that is next step of 1, right? Okay. Okay, so first step, you will eat everything as 0, including this one. So if this one, as you can see, there are 2 of them here, right? But you have to consider that all of them are 0. So the first step look like this, right? So they are all 0 first. So 0, don't care, 1, 0, 0, 1. Okay, and then you circling it. As you see here, there will be 2 more here, 1 and here, right? That's the first step. So you get these 2. This gonna be this one, right? And this one. So that will be B, C bar, and this one gonna be A, B bar C. Okay. And then the second step, consider each cell to be 1 at a time, because you can move to other states, A, B, and C. It can move just from one state to the other state. That's why each variable has to be just 1 at a time. For example, this step 2. So step 2 can be, for example, when the CP bar, when this cell is 1 and the other still 0. Okay, and try to circling it as best possible. As you can see, yeah, this one is already the old one, right? So that's nothing new, but this one is new. Okay, so have to circling this. Yeah, but this small still there, right? You don't delete this. Okay, you still keep it there. Still keep it there. Okay, but the green one has to be imposed upon. Okay, so this one is what? This one is B bar C, right? B bar C. Given that this one is this cell is 1, is true, which is the CP bar is true. So that's why it's come out that's this one, and CP bar is true. Okay, or CP bar equal 1 or true. That's why you have to circling and add with the CP bar. Okay, and the third step, consider what? The second step, you can say that this is 2.1 and 2.2 is step 1, right? 2.2 is the same thing, but now consider the other one, which is this one only, to be 1, and the rest is 0. Or the other variables, this one is going to be 0, and the rest is the same. Okay, and now try to try to circling it, as you can see here. So the list is the same except that this one. Okay, so yeah, that's the best one that you can do, and you can see that there are also remnant from the same. These are the same, right? So that is the only one that is different. So this is this circle is this, right? Which is A bar B. Okay, and given that this cell equal is true, is equal to 1. That's why you came out as A bar B, and this one is true or equal 1. Okay, that's why you came out as this. Okay, this is how you circling it and get the things out. Okay, when you do this in the exam room, please make sure that you circling everything's right. Okay, remember that the first step, you need to circling the one that is everything is 0 first and leave it there. Okay, don't do optimization. Okay, don't do optimization. Okay, yeah, something like this. All right. The third one. Okay, let's try the third one. Okay, let's try it here. The third one. Okay, that's the third one. Try it here. Let's move this to the side a little bit. Ah, mm, okay. Let's try this one first. As you can see, we draw the first step by looking at all this assumed to be all 0 first. Okay, and we look at the rest by looking at the one that we can vary. And here you can see that we cannot do better than this, right? So that's the first step, which is came out as BC bar. Okay, step to step 1. Okay, and then step 2, consider to be 1 by 1 at a time. For example, if this is 1, the other is will be 0, 0, and see if we can do optimization. As you can see, we can add here, right? Okay, so we can add here, and that will be this one. Oops. Yeah, the green one is what? A bar B bar. Given that CP is 1, so that is A bar B bar, and CP is true, which is CP bar. Okay, so that's the green one. Okay, next, consider the third one, which is PDR. When this is only 1, that is 1, and the rest is 0. Okay, and we try to do it as best as we could. And since this is what you call it, don't care, right? So we can actually do this. Okay, when this is 1, it is don't care. So you get the third one, and this one is BC bar. So that's a BC bar. Given that PDR is true, so it's N, yeah, N, PDR is true, so that's BC bar. And the fourth one, when this is only the one that is true, which is 1, right, which is 1, and the rest is 0. So you can see that this is 1, this is 0, and the best one that we can do is this, right? Okay. So we will never be something like this, right? We will never be something like this. You can never be two variables in the same brackets. There's no way that you can do that, or even 3 or 4. That's not possible. Okay, so that's why you can have only these things. Okay. Okay, except that it's possible that they are in the same table, and that can be possible. For example, if this is this, right, and this is let's assume that is this and CR here and CR here. Yeah, this is possible because CR can change at the same times. Can it? No, sorry, you can't. You can't, because each cell can change one cell at a time. You cannot change more than one cell at a time. Never. Okay, you can jump just one cell at a time. Okay, that's how you arrive at this. All right. Okay, so I guess we take a break a little bit. Okay, then maybe 5 minutes, and then come back, and I'm going to show you if we use the JK instead of the D flip-flop. Okay, so what we're going to do, maybe 5 minutes break. Okay. Okay, let's come back to our lesson. Okay, so you guys, can you guys hear the sound? Okay. 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 So those are the examples that we use the D flip-flop for our control. So basically, what we have here is already the hardware. So if you want to generate or build the hardware, this is going to be look like, right? So it's going to be look like this. Oops. So you have the D flip-flop. You have 3D flip-flop, right? What we did in the states diagram. Oh, okay. Move this a little bit further, and you have the flip-flop. Okay, sorry. Clock. This gonna your design, whatever, up or down, and you have the D, DA, DB, and DC. Okay, and then you can build the circuits from here. DA is AC bar, so that's AC bar, right? With A bar B and A bar B and what, and equal plus constant. Go in there. Okay, and this is A, B, and C. Okay, so basically A, B, C was fed back there, and DB is more complicated. So you get this equation here. Okay, you get this equation here, but you can generate a graph over here. Yes. 1, 2, 3, 4. Bar B equals sine B bar C, CP bar, PC bar A bar C, right? And then go there with the big R and then enter B. Okay, so this is what we generate for, right? And these signals come from outside and also from the state itself. Okay, and this is another one that go into PC. All right, so this is how to generate the system controllers the one that we saw here. Okay, with all the signals that can come in and go out. Okay. Yeah, of course you have to generate a big chunk of ABC that going in with something and generate the output signal, right? Which is these things are, like you can see pop, accumulate nickel AC. So those will generate pop, nickel AC. Okay, so these are the signals that came out. Okay, and how you going to compute it? Of course, based on drop. For example, drop this when you are in state D, drop this when you're state E. Okay. All right. Next, I'm going to show you how to do this with using the JK flip-flop implementations. Okay. So basically, we start off with the same thing with state A, B, C again, right? And we have to do the state analysis again, but this time for okay, and this time for JK flip-flop. Okay, let's go back there again. So state A again, state A. For example, state A, which is 0, 0, 0, right? To state A and F. Not A and F, it's A and B, right? 0, 0, 1. Okay, so it's going to A and B, 0, 0, 0, and 0, 0, 1. Okay, so from 0, it's going to go to 0, right? Okay. For D flip-flop, you just insert 0 there. But for JK flip-flop, now you have to consider both JK at the same time. So you need the JK flip-flop excitation. Okay. And of course, you start off Q. And Q plus is the state that you want it to go to. For example, when you got 0 and 0. But now you have to control JK such that when you put JK and when you see the edge coming, then JK with the JK, then Q will evolve from 0 to 0, right? For example, if you want the O1 is 0 and you want to 0, you have two choices. The first one is you can see that, hey, this is the same. So 0, 0 mean do nothing or memorize, right? If you still remember JK flip-flop, 0, 0, Q. Q plus is Q, which means that remain the same. 0, 1 reset. The new Q is going to be 0, 1, 0 is set, right? And 1, 1 is toggle, which means that it's the Q bar. Or if Q is 0 before, then it's going to be Q bar. Okay, so those are JK flip-flop characteristic. Okay, so if you want 0 to be 0, then it's going to be 0, 0. Or you intentionally what? Reset it, or you can use 0 and 1. Okay, so together you can see that when you summarize this, JK, this one need to be 0, but K can be neither 0 or 1. So this is going to be X, right? 0X. Okay, so if you want to change it from 0 to 1, you have two choices. One is to set it intentionally, so it's going to be, 0, 1, 0, 1, 0, or toggle it is going to be 1, 1. Okay, or this mode, right? So that's summarize is 1x. Okay, 1, 0, 1, 0. This is reset intentionally, can be 0, 1, or toggle. So it's x 1, right? And 1 to 1 is going to be 1. Okay, it's going to be remaining the same, or what? Or set it intentionally, which is set it intentionally, so it's going to be 1, 0, right? So together it's going to be x 0. So This we call the JK flip-flop excitation. So in this case, you have to consider J and K at the same time. For example, if the O1 is 0, the new one is 0, what you put in there must be 0x. So 0x, which means that JAKA has to be 0x to remain the same. And you can see that when you go back there, it's going to be 0 and x. Remember that this is don't care, right? So that is 0x, don't care. Okay, by doing this, the same thing. So this is going to be 0x again, right? 0x, 0x, okay, 0x. And 0 now is going to be 0 and 1. Okay, so 0 can be changed to 1 only when what? When this one has to be 0 and 1 has to be 1x. If you want to change the states, right? Okay, so it's going to be 1x. But where you get the 1 from? Of course, when you change the state from A to B, which is CP, right? Which is CP. As you can see, A to B can happen only when this CP is present. So yeah, it's going to be 1x, but this one come from CP. So it's going to be CPX. Okay, if CP is 0, you can see if CP is 0, then 0x is going to be remain as 0, 0. Okay, so that's why JC is equal to CP. JC, KC is CP and X. Okay, so you put CP here, right, and X here. All right. Okay, so that's how you consider each one. I guess I could show you maybe one more examples that we can do. Yeah, the other thing is the same. Okay. Yeah, maybe I can show you this one. Okay. For state C, okay, for state C to D, E, and F, right? State C is this 0, 1, 1. Let me try this 0, 1, 1 to A, which is 0, 0, 0, and then 1, 1, 0, and then 1, 0, 0, A to D or F. Okay, this one no problems, right? State 1 to 0. So JC, KC is what? 1, 1 to 0, JC 1 to 0, JC is X1. Okay, so this one is X1, no problems. X1, you can see this is X1, X1, X1. Okay, no problems. Yeah, maybe I just write here. Okay, so that's X1. Okay, and the next one is this one, right? As you can see, it will change from 1 to 1. It can change, remain 1 to 1 when this is X0, X0, okay, X0, but of course, X is X here, X is X, okay, as you can see here, X, but 0, hey, it's 0, right? But 0, you don't have 0, you have what? This is going to be true when you jump to what? When you jump to, when you jump to D, okay, from C to D, right? But C is this, and D is this, and it can jump only when sigma equal, right? So true when this is true. So if you want a 0, then it's gonna be what? It's gonna be this 0 is gonna be bar, equal bar, or you can say equal bar, or not equal. Okay, or you can consider this as well. If 1 to 0 change to both, right? 1 to 0 change to both. The first one is what? When one A to C, or C to A, sorry, C to A. This is when this happened when this is greater, I think, right? 1 to 0. This happened when this is x1, okay? And this one can happen in two cases. The first one is when this is greater, I think. One is greater and one is less than, right? Okay, one is greater and one is less than. Or you can say that this is x with greater and less than. Okay, or you can say that this is not equal. This is not equal. Same thing. No matter where you come from, this way or this way, it's going to end up the same things, or not equal. That is mean that equal with the bar, or you can say not equal, or this is equivalent to this plus this. From the state, as you can see here, yeah, one is Z back to A, which is this root. The other one is C to F, which is this root. Okay, so either this root or this root, which means that less than or plus, or means not equal, right? Same thing. Okay, that's why this, you can write this as not equal. Okay, and for A, yeah, for A, 0 to, you can say 1 and 1, right? And 0 to 1 is 1x. 1x. JAKA is 1x. And where is 1 come from? C to A, C to D, or C to F, right? C to D and C to F. I think this is greater, equal, right? That's why it came out as greater or equal. Okay, and 0, or don't care. Okay, that's how you generate all this. And then we can circling with the same principle. Okay, first do the one first. Don't care, don't do the don't care. Don't care has nothing. So if you consider this is 0, this cell, you don't circle anything, right? Next, first step, but plus nothing. Okay, when this is 1, you can see that we can actually circling this. Can we? Oh no, we can do better, right? Because this also don't care, so we can do this. This guy is B. So if B, given that this one is true, so that's why B and this one is true. Okay. And again, this is same thing. 1 only, you can draw this, right? Because it's don't care and you don't have any variable left. That's why x equals Z. Okay, next is this one. Okay, again, first step is looking at when this is 0 first and try to do this as best as possible. So this is the best one. This is AC. Okay, and then when consider this 1 or active, okay, then you have what? You have this only, right? That's why you got C and CP. Is it? Oh, sorry, no. You can do this. This is 1 and this is 1 as well. So you can actually draw the big one. The second step. This is C. And C given as CP is true. Okay. So that's how you do it. The last. Try this one again. Okay. So there's no 1. Consider that this is all 0. So you don't have to do anything, right? And then consider that this only one cell that is 1. Then you can draw this, right? Other cells still 0, right? So you get this one is A bar. So this A bar with CP is true, right? And then the next one, when this is 1 and the rest is 0, so you get this one 0. So that's B. Okay. And then the last one, remember that this is still 0, right? And this 0, and consider that this only one, that is 1. Then you have only one chance here. That's it. Okay. And that will be AB bar. Okay. Again, you can create a circuit like this, okay, with the rest of this, right? And this is the output generator, so that the states, right? When this state come in, then you generate all these signals according to the states, okay? So these are the implementation directly. Okay, yeah, forget to tell you what this method is called. It's called VEM, variable entrance map, sorry. It's called VEM, variable entrance map method, okay, especially for this kind of method, okay. Yeah, and once you created the controllers and then you can put everything together, then you can have the pop machine, okay. Any questions on this? I know it's a little bit harder, and the rest of these chapters will tell you variations of how you can generate the microcontrollers. For example, you can use decoder for the states to reduce the SSI logic, okay, and use bank of flip-flop instead. Yeah, you can do this, okay, as well. Yeah, it's the same thing. Yeah, you can see you can generate state C if this is true. Okay, by just insert the flip-flop in there, and we give you if this is true or state A is true. So it's decoder, right? I don't know if you still remember decoder. Decoder gives you something like this, right? For example, if you have 3 bits, A, B, C, if we give you 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So this is decoder. When, for example, when this is 0, 0, 0, only this one will be active, or 1, 0, 0, 0, and the rest is 0, right? Or if this one is 5, means that number 5 will be active and the rest will be 0, right? So basically this will tell you which state are they, right? And if you assign this, you can see that 0, 0 is state A, right? This is state A, and this is state B, for example, C and blah, blah, blah. Okay, so state A means the output of the decoder that correspond to this, okay? Yeah, state C, state E, state D, for example. Yeah, you can use this one to as well to replace the flip-flop, okay? And then do decoding directly, okay? That's what it say, okay? Or you can use multiplexer, okay? Next state decoder together. To select what the next state variable is. Okay, I'm not going to cover this. Okay, another interesting method is to use BROM and PROM. Okay, we call this one the lookup table. So you don't have to compute anything, because what you have is you have a box of memories, and these memories you get the address in. What is the address? The address is ABC together with the input. So these are your input together. The input are the address of the RAM. This is on the address side. And what's released at output is the already computed. So these are already computed. Because you know where it's go, right? For example, 0, 0, when this input is this, then where you go, you know. For example, when I0 or CP is here, then you know that you're going to go to B, for example, right? So you just compute everything and then just store the result here. So once you have the input, it just turn over the page. For example, when you know the states 001 and you know what input is going in, then you know the answer right away. What type of signals going to be released at the other side, or you can say that is pre-computed. So it's very quick. Okay. The drawback is that this is going to be very huge. You need a big storage of memories. For example, this is what 1, 2, 3, 8, right? 8 input, 8 inputs, and how many outputs? 8 outputs. Ooh, how many bits are there? So here you have what? How many storage? 2 to the 8 lines, right? You have 2 to the 8 lines of this because you have 8 inputs, right? Then you have 2 to the 8 lines, which is 256 lines, right? And then each line has 8 bits. So it's 256 location, and each location is 8 bits. So you need what? You need a ROM of 256 bytes, okay, in here. At least 256 bytes. So that is number of storage, that total number of bits that you need to store here. That's the total number of bits. This is 256 bytes. Okay. Okay, so basically you program the prompt, right? And you have the input that pointed in states A, B, C, right? And then with the input that come in, and then you can see that you actually generate the output present state and the output signals that came out. Here you can see, right? Okay. Or you can use PLA, or you can choose shift register, which is another technique. Or use even the counter. You can count up, count down. For example, here you count up, right? Here you count up, load 3, and then you count down, count up. Here you count up, here you count up, right? Yeah, something like that. Okay. So you can count, load, and yeah, whole count implies load, and then override, or you mean that? Okay, here you need to control the signal, but it's the same. If it's 1, then you do something. Okay, so this anyway, so these are you should go and practice this method a little bit. I give you the activities so that you guys have to do it. I give you about 1 week to digest and do some of this. Yeah, let's go there. Okay. Yes, that's in activity 8. Okay, so you can try this and then using VEM, design the state machine using the state diagram. Okay, yeah. You can assume the D flip-flop is used. Yeah, try to do that. Okay. Yeah, it is same as pulse. Okay. Okay. Any questions? Oh, I also put up the example for the last 3 chapters. You can see this in the exam preparations. So now you can have sample questions, some of which can be asked in the exam, the final exam. Okay, yeah, something like this. Okay, you can practice this, right? Okay, and I also give you the solutions. Yeah, hopefully everything's right. So if you find some mistakes, please tell me or inform me as soon as possible. I'm going to correct that. Oh, yes, popping to the network, I think. Yeah, give you with the solution. So don't look at the solution, try it first. yeah, hopefully you try it first and then yeah, see if you can do it, right? Something like this. Okay, so if you can do this yourself, then it's probably like you'll be okay in the exam. Yeah, okay. Okay. Any questions for today's lecture? Right. Yeah. If not, then I think it's I'm gonna finish for today's lecture and see you on Monday for our last lecture. The last chapter will be easier. It's more like storytelling, I guess. Like generals. It's more like a description, more like descriptive. Okay. Today is hard actually. You need some time to digest all this. Okay. That's why I give you about 1 week for the activities. Okay. Any questions? Then if not, I'm gonna let you go for today. And thank you for coming and see you on Monday. Right? Okay.